The R code that I show in this video is available on Elms, and you may want to take a minute to download it and open it if you'd like to follow along on your own. In this video, we're going to put everything that we've done so far together in R scripts. By the end of this video, you should understand how you use R scripts to string together many commands in R, and also what the advantages are to using R scripts over typing commands directly into the console. So by this point, you should have a basic understanding of the expressions in R and the data types used in R. The fact is, accomplishing meaningful tasks in R generally requires more than one expression. To string these expressions together, you should create R scripts to execute all of them in a sequence. The easiest way to think about R scripts is to think about the procedural paradigm. Remember, this is a recipe that takes you from start to finish with each step along the way. So what you should do is think about what you're starting with in an R script and what you would like in the end. Then you fill in the steps that you need to get from the start to the end. You should include each of those steps in order in your script. So I'd like to use an example where we're going to think through solving a problem using an R script. In this case, suppose you're thinking about buying a new light bulb. It goes in a lamp that you use exactly 8 hours every day. The current light bulb you have is an incandescent light bulb that uses 60 watts of electricity. You can replace it with a compact fluorescent light bulb that only uses 15 watts of electricity, and it costs $2.15. Electricity isn't free. It costs you 23 cents for every kilowatt hour of electricity that you consume. And my question is, how long would it take for the energy savings to pay for the bulb? This isn't a course in energy economics, it's a course in data science, so I'll actually give you all the calculations that you need here. You'd start out by computing your energy savings per day, which is 60 watts minus 15 watts. That turns out to be 45 watts, times the 8 hours that you would use the bulb, which leads to a total of 360 watt hours. Then you go on to think about the money that you save every day. Again, there's 360 watt hours that you're reducing your electricity consumption. Your electricity is priced in kilowatt hours, so you need to convert that from watt hours to kilowatt hours by dividing by 1,000. Then you multiply by the 23 cents per kilowatt hour that you're paying for every kilowatt hour of electricity, and that comes out to you're saving 8.28 cents per day. Now that you know this, you can calculate how long it will take you to pay off the light bulb. The light bulb costs $2.15. You divide that by your per day savings, and that gives you the total number of days it would take to pay off the light bulb, which, as it turns out, is 25.96 days. Now, how might we implement this analysis in R? So I've actually written out all of the R code that you would need to do this. First, what we would do is list all of our assumptions. This makes it easy for anyone looking at your R script to know exactly what assumptions are feeding into your calculations. This improves both the transparency of your work because your assumptions are obvious, and the reproducibility because everyone knows exactly what those assumptions are. So on the left-hand side, I have some prototypical R code here where I define several variables, old watts being the wattage of your old light bulb, new watts being the wattage of your new light bulb, hours per day is the number of hours per day you're using the lamp, new cost is the cost of the light bulb, and elect per kWh is the price of electricity in every kilowatt hour. Then what I do is I take all of these mathematical calculations I have on the right and implement them in R code. You'll notice that my R code on the left-hand side includes comments to tell me everything that's going on. So looking at this code, it's very easy to see what each step does. Also, it's very easy to see what steps are doing because the variable names are very descriptive. They tell you exactly what is in the content of the variable. So step 1 asks how many watts I save per day. And again, that's the wattage of the old light bulb minus the wattage of the new light bulb. And I take that quantity and multiply it by hours per day. I then save that result in a new variable, which is watt hours per day. And that's holding the 360 that you see in the calculations on the right. In step 2, I compute the money saved per day, which again is where I take the electricity consumed per day and multiply it by the electricity cost. Now remember, my initial calculation was in watt hours per day, but I pay for electricity in kilowatt hours per day, so I need to make a conversion. I do that by dividing by 1,000, but also note that my comments remind me about that, so anyone looking will see why I'm including that divide by 1,000 in my expression there. In step 3, I implement the last calculation, where I calculate the number of days until it's paid off, and again, I divide that variable new cost by the dollars per day that I calculated in step 2. That gives me a new variable, days to pay off. Then after that, I print it out to the console using the print command. So let's take a look at what this would actually look like in RStudio. As you can see here, I have a script. There's a label at the top that tells me exactly what this script is. It's the sample code for this module of video. But then I follow with everything that is in that slide. So I show you the assumptions at the top. Then I have each step clearly labeled with clear variable names. and then finally the print command at the end to print out the result of this calculation. If I would like to run this in R, I select all of this code, I press the run button, R will run each of the steps in order, so I can go down to the console and look at the output. It's a good idea to always scroll through all of the output to make sure there were no errors. And as you can see here, all of my code ran through with no errors. And at the end, I get the end result of that calculation, 25.96618. So you've seen how I've implemented this in an R script. What makes this a good approach? First of all the steps that get you from the start of the calculation to the finish are recorded in a single place. The purpose of each step is clear because I used descriptive variable names and I included comments before every step. It's easy to see and dissect each step in order. It's also very easy to make changes if there's something I'd like to change about the calculation. And it's also very easy to restart the calculation from the beginning. Now, why is all of this important? You might not make every decision just once. And in fact, most decisions are made over and over and over again. So in this case, let's say you run this calculation. You decided you were going to buy the compact fluorescent light bulb, but then right before you check out, you see that there's an LED light bulb for sale. This only uses 8 watts of electricity, but it's more expensive. It costs $4.25. How long until you pay off that light bulb? Instead of redoing all the calculations on your own, or typing them all in one by one, all you have to do, because you've encoded this in an R script, is go back to the beginning of your script, change 2 of the assumptions, and rerun it. This is the real power of integrating your workflow into R scripts. So let's actually go through and do that new calculation in R. So the 2 changes that I need to make, the new light bulb, instead of using 15 watts, only uses 8 watts. So I'll change the 15 to an 8. Second, instead of costing $2.15, the new light bulb costs $4.25. So I'll change the new cost variable from $2.15 to $4.25. Then all I have to do is select all of the code, rerun it. Let's take a look in the console. It's always a good idea to scroll through your code to make sure everything ran correctly. There's no errors. And then what you can see down here at the bottom is the new result of the calculation is the LED bulb would take 44.42 days to pay off. So again, I hope this elucidates the power of R scripts. When you're making decisions multiple times and the parameters are changing, it's very easy when you encode your entire workflow in scripts to make changes to the assumptions, make changes to the underlying data, update your underlying data, then rerun your entire workflow and receive new results to help you make new and updated decisions. So the R script that I showed you is about 25 lines of code to perform this calculation. You could actually perform that exact same calculation in R using the code here that I have on the right, which is just 1 line. So I've asked you to do a lot more typing, 25 lines, a lot more characters, to do something that you could just accomplish with what I have here. But how does this code reflect on the core principles of data science? First, is it reproducible? I'd say the answer is yes. Anyone who has access to this piece of R code can run it and will get the exact same result. R is deterministic in its calculations. Running this piece of code, no matter whose computer you run it on, will always produce the exact same result of the calculation. So the code is reproducible, but is it transparent? Does it reflect the core principle of transparency in data science? Here, I'd say no. This calculation is completely opaque. If you were to look at this, you would have no idea what is going on. It would take you a really long time to dissect the calculation. If I were to ask you to change the wattage of the new light bulb or change the price of electricity, it would be very, very difficult to do this. Whereas with the 25-line R script that I showed you before, it's very easy to figure out every component that needs to be changed and rerun it and have confidence in your results. This is a core difference between reproducibility and transparency in data science. Again, transparency is very much about the why, and looking at this 1 line of code, the why is not obvious to anyone. So again, a best practice in data science is to implement as much of your workflow as possible in scripts or programs, and this course will use exclusively R. You want to separate each step across lines with comments explaining exactly what you're doing, what your assumptions are, and maybe what you were thinking, what your intent was as you write the code. Again, this makes it clear to anyone else reading your code, including yourself in the future, what's going on at every particular step. That makes updates and changes easier in the future. You may use many scripts to connect the tasks in your workflow together. Workflows can be large and expansive. It's best to include a single task in a single script file and then connect those together. If you do that, it's important to document how each script fits into your workflow, where it is, and when it should be run. So at this point, you should have a good overview of how you should be using R scripts in your data science workflow.